On board merchant ships, we usually operate at 3-phase, 440 volts, 60 Hz alternating supply. But the object of this video is to understand why we use high voltage on board ships. What are the advantages and what do you gain exactly by using high voltage? For that to understand, we have to know how high is the voltage used on board ships. So with respect to the marine environment, low voltage is said to be any voltage or the ship's operating voltage which is less than 1000 volts, and high voltage is termed as any voltage or the ship's operating voltage more than 1000 volts. So with respect to this, we currently have at this point of time 3 ranges of operation at high voltage. One is 3.3 kV, and the other is 6.6 kV, and the third is 11.1 kV. So these 3 classifications are usually encountered on board merchant ships. 3.3 kV is the rarest to find, and we have some container ships or some specialized vessels like research ships, and 6.6 kV is used mostly by the LNG ships, both motor and steam vessels, and 11.1 kV can be found only on board passenger ships or some drill ships or even sometimes some FPSOs. So let's now see why we use high voltage, either 3.3, 6.6 or 11.1. Now let's start with the basic. We all know that the Ohm's law states that power in any circuit is V into I. I'm just writing the formula to understand it easily, and if it's going to be a 3-phase circuit as we used on board, it's root 3 V into I into cos phi, and this is being the power factor of the load. So now for time being I'm going to neglect this cos phi factor and root 3 just for simplicity and understanding. So I assume P is equal to V multiplied by I. Now let's understand for a given power, let's say 440 kilowatts is the power. I'm going to operate the ship at 440 volts. So what will be the current? It will be roughly 1000 amps. I have neglected the cos phi, that's the power factor. So to operate a ship at 440 volts, I have to design the cables and everything for 1000 amperes to achieve a load output of 440 kilowatts. Now I'm going to operate the ship at, just for example, let's say 1100 volts. Now the required amperes drops to 400 amps. That's fantastic. So I just need to design the cables just for 400 amps. And if at all I increase the voltage to 11,000, and now the required amperes is just 40, which is still less. So what we can find is by increasing the voltage, or I'll show it over here, V into I. So by increasing the voltage, the current drops for a given power on board a ship. So as I keep on increasing the voltage, I just have to design my entire circuit, feeder circuit, and let's say protection devices just for 40 amps. That's a great advantage, right? The cable size can be smaller. Obviously it's known that you all know that the cable what I'm going to use for 1000 amperes will be thicker, and 40 amperes will be very thin. So I'm going to let's say save huge amount of money over it, or space, weight, everything. Now let's talk something on losses. I'm not going to talk on iron loss or copper loss individually. Generally losses, which is majority, is contributed by I square R. R being the resistance of the circuit or load, and I being the current in the load circuit. Now R remains same. Let's say I have a ship with fixed electrical motors, fixed load like galley, heating stuffs, lights, etc. So R is fixed. With 440 volts, I'm gonna have, let's say, previously we have calculated with 440 volts, we're going to have 1000 amp circuit. So with 11,000 volts, we have 40 amp circuit. Now just bring this 1000 amp in this formula. If the amps is going to be too much high, let's say 1000 amps, so my losses are going to be square of the amperes. 1000 square will be my losses, which is huge. However, if I say, let's say I design my circuit for 40 amps, when you put it in this formula, now 40 square is comparatively very less when compared to 1000 square. So my losses is going to completely depend on square of the current. That's the reason we reduce or bring down the current by increasing the voltage. And let's now see about the short circuit or fault protection circuits and how we design or what are the advantages we get by using high voltage. Let me draw a circuit, simple circuit for you. This is generator 1 and this is the circuit breaker, and this is the bus bar, and this is going to be supplied to the load. Okay, and I have one more generator, and this is the circuit breaker, bus bar, and this is the feeder circuit breaker, and a similar load. I'm showing two bus bars just to understand the concept. Actually, on board ship you will have maybe bus bars connected together. So let's say this generator number 1 is 1000 kVA, 3-phase, 60 hertz, and it operates at, let's say, 415 volts. I'm not taking 440 just to get a fresh idea. I'm just saying 415 volts. Now this generator is also 1000 kVA, 3-phase, 60 hertz, and let's say it operates at 6600 volts. Now both the generator and the bus bar or the supply circuit has equal load. Let's say some 800 kilowatt or something. Let's say we'll assume it. Now the full load current for this circuit, I'll just change the color. Full load current on this circuit will be roughly 1400 amp. Now you got to calculate the full load current by using the formula P power is equal to √3 V into I into, if you want you can put cos phi, but I neglect it now. √3 VI, that's it I'm going to use. So I get the full load amperes to be 1400 amperes. So now what I have to do is to protect my generator and all of the circuit, let's say the supply circuit and the feeder circuit, I have to design my protection devices roughly, as a thumb rule, 10 times the full load current. So 10 times of 1400 amps is 14 kiloamperes. So I have to match my circuit breaker and other protection devices for 14 kiloamperes. Now with a similar structure and calculation, now we're going to calculate for 6600 volts. Alright, so similarly calculate with the help of the formula √3 V into I. You'll get the full load current for the generator, which is operating at 6600 volts, to be just 88 amps, roughly, let's say 90 amps. So As a thumb rule, again we have to design just 10 times the full load current. So I have to design my circuit breakers just for 90 into 10, that is 900 amps. That's it, which is going to reduce the size of the circuit breakers and protection devices and help to save a lot of cost, a lot of money. So that's the main advantage we get by increasing the voltage. So it is for this reason we operate at high voltage on board certain ships.